Alright, so in this video we are going to discuss about solutions of a differential equation. Now I'm not going to solve them, but I'm going to explain their properties, and let's have a discussion about how they look like. Okay, alright, so before, let's start from an algebraic equation. Now if they ask us to solve this equation, we all know intuitively the solution here for this equation is 7. Now once you find that, that's it, we are done with the equation. But for a differential equation, it's not that simple. Okay, now let's look at a differential equation. Dy over dx is equal to x square. Now for this differential equation, you're looking for y, right? Y is the unknown. We are solving for y. Now we all know y is a function of x. X is the independent variable. Y is made out of x, something like y is equal to e to the x. Okay, so that's an example. So we have to look for this y. Now y is a function, so solution for a differential equation is a function. Okay, now I have to be careful there. I cannot say the solution, because a differential equation can have infinitely many solutions. Okay, keep that in mind. Or sometimes a differential equation can have a unique solution. That means a one solution, just a one solution. Like for this equation, the solution is 7. That's it. Or a differential equation sometimes might not have a solution at all. Okay, so 3 cases. Now we all know solution for a differential equation look like a function. Now that's not simple enough. I mean, here we solve this algebraic equation and we said solution is 7, but for differential equation that's not enough. Let me say you why. Now to be a solution, so a function, if a function want to be a solution for a differential equation, now I'm just using singular terms. Okay, a solution, a function, but it's valid for plural version also. Okay, I'm sticking into singular version just for simplicity. So any functions, if they want to be a solutions for a differential equation, they have to satisfy certain conditions. So let's look at them. So dy over dx is equal to x square. Now let's say I claim that y is equal to x cube over 3 is a solution. Now I'm saying that. Okay, you don't have to worry how I got there. Now, how do you verify that it is a solution? How do you prove whether I am correct or wrong? Okay, so let's say someone comes along and says 6 is a solution for this equation. How do you verify that he is wrong? We intuitively know that 6 is not the answer. Well, what you do is you substitute 6 back into the equation. So 6 plus 5 is 11 on the left hand side, right? But on the right hand side you have 12. So left hand side is not equal to right hand side. There you go. 6 did not hold for equation. 6 did not satisfy the equation, right? So same can be done for differential equations. Let's see. Let's substitute x cube over 3 back into the equation. So let's see what happens. So left hand side. So in the left hand side of the equation, they ask us to take the derivative of y with respect to x. So let's take the derivative. So dy over dx, if you differentiate, if now we take this 3 out, 3x square over 3. So the left hand side is derivative of y with respect to x is actually 3 cancel out, x square. Now what happens? Is it equal to the right hand side? What do you have in the right hand side? Take a look. So the right hand side is also x square. So left hand side equal to right hand side. So then yes, x cube over 3, y is equal to x cube over 3 satisfy the differential equation. So it looks like x cube over 3 is a solution. Okay, so let's hold on there. Now one more thing. Let's say someone says that y is equal to x to the 4 is also a solution. How do we prove that it's not, or it is? So let's take the left hand side. Derivative of y with respect to x is, you take 4 out, so it's 4x cube. Now do we have 4x cube in the right hand side? No, right? 4x cube is not equal to It's not x square. So x to the 4 didn't satisfy the differential equation, so it is not a solution to begin with. Okay. Alright, so that is how you verify whether a given function is a solution or not. You just substitute it back. Okay, so I said that's not enough. Then what else you need? Okay, so you have to say, where is your solution living? Where does it lives? That means we had y is equal to x cubed over 3 as a solution. Now you have to give an interval for x. Okay, valid x values you can take and perform this function. Okay, the valid x values, or your function should be continuous on an interval I that you propose. So I propose the interval for x values is negative infinity to infinity. Okay, so is x cubed over 3 continuous in the interval negative infinity to infinity? Yes. Okay, so then that's it. That is how you express a solution for a differential equation. It should satisfy the differential equation and you should give an interval where the function is continuous. Okay, not only that, not only the function, but its derivatives also should be continuous. What do I mean? By derivatives, I mean you have to look at the order of the differential equation. Now here the order of the differential equation is 1. Okay, now understand it. This is something that makes sense. This is not super mathematically complicated. Now if you say y is equal to x cubed over 3 is a solution of the differential equation, in the differential equation you have taken the first derivative, so you should be able to differentiate x cubed over 3 at least one time, right? Otherwise it doesn't make sense, right? So your solution should be differentiable, at least n times differentiable for nth order differential equation on the interval. Okay, in the interval, inside the interval. Okay, so let's look at at a better example. Dy over dx is equal to 1 over x. This is a good example. Now let me say solution is y is equal to natural log x. Alright, so let's verify. Left hand side, what is the derivative of y with respect to x? If you differentiate natural log x, it's 1 over x. So on the right hand side we have 1 over x, so it satisfies the equation. First test passed. Then give me an interval for y is equal to ln x. So give me an interval for x. Can we take negative infinity to infinity? Here's my question for you. Think, pause the video and think. That's the best way to learn. No, right? Why? What is the reason? So at first, can we take the natural log of a negative number? We cannot, right? So natural log x, natural logarithm is not defined for negative numbers. So the interval should be, let's say, from 0 to infinity. Okay, I use the close brackets here because we don't know what happens at 0. We cannot definitely take infinity. But how about 0? Is natural log 0 defined? No, natural log 0 is also not defined. Okay, and on the other hand side, derivative of natural log is 1 over x. 1 over x is not continuous at 0. X is equal to 0. So that's another reason. So your interval should be, we cannot have 0 also. So your interval for the solution is from 0 to infinity. That's a better example, I think, than the previous example. So when you say a solution for the differential equation, you have to give an interval. So solution for a differential equation comes as a pair, the function itself and the interval. Also, I didn't use the plural version, functions and their intervals. Okay, so that's the important thing when you talk about a solution for a differential equation. It has to come with an interval where the function is continuous, the solution is continuous, and also its n derivative, at least n derivatives are also continuous. us. Okay, all right, so I will see you in the next video. Thank you very much.